morning. Today we are going to discuss undecidability, undecidability and halting problem of Turing machine. See, suppose that we have a Turing machine. This is a Turing machine M, and suppose that an input is given W, and if it is a valid input, it is said to accept this. That means it is accepting the string, that is accepting the string. That means if it is a valid string according to this Turing machine, this is a Turing machine, and that will accept the string if it is a valid input. And sometimes there is a possibility for rejection, reject. And in some cases, it keeps on processing the data. That means it keeps on processing this W and it will not halt. And it will not say either it is accepted or rejected. That means in some cases all the inputs, that means if W is a valid input, definitely that will be accepted. And in some cases there is rejection also. That means it will go to a rejection state and it will report that it is not a valid string according to our Turing machine. And in some other cases, there is a possibility that it keeps on processing this W and it cannot come to a conclusion whether that can be accepted or not. That means after 2 minutes, after 3 minutes, after 1 month, after 2 year, 3 year, or after 2000 years, it keeps on processing that W, and after 3 years that can accept it. That means we cannot say whether that string can be accepted or rejected. That means if W is a valid string, definitely that will be accepted. But we cannot say whether that is accepted within a stipulated time. That means that is the halting problem of Turing machine. That means if a string has to be rejected, then definitely that a Turing machine has to go to a rejection state. But here in this case, most of the Turing machine is having an accepting state. As an accepting state, if it is a valid string, that will be accepted. And if it is not a valid string, it keeps on processing the data, processing the string, and it cannot halt. That Turing machine is not halting. As per the definition of Turing machine, if it is a valid string just to be accepted. There is no possibility, there is no constraint like it has to reject the string. There is no condition, something like that. If it is a valid string, definitely that will be accepted. And if it is not a valid string, uh, it keeps on processing that W, and after some time, after we cannot predict, or we cannot have in such time constraint we have to report or something like that. So in that case, we say that it is looping. That means it is looping. That means loop. That means it is in a loop. When we are comparing this Turing machine to an algorithm, suppose that we are writing a good algorithm, then after processing your input, it is printing something, or if it is generating yes or no, that means definitely that Turing machine will halt. That means your program will halt. If if your input is right, then definitely you will get a result. And if it is not a valid input, then there are cases for some algorithm it will loop. Okay, that is a Turing machine. That is a halting problem of Turing machine. And generally speaking, a Turing machine is accepting valid string and it is not rejecting. That means that is the halting problem of Turing machine. Halting problem of Turing machine. And the language accepted by a Turing machine is said to be recursively enumerable. Recursively enumerable. Language accepted by a Turing machine is said to be a recursively enumerable language. And now we are going to discuss what is a recursive language. Recursive language means, suppose that you have developed a Turing machine which always holds. That means it is accepting or rejecting the string. That means a Turing machine which is not having any halting problem, that means either it will accept or reject the string. Either it will accept or reject the string. And suppose that you have a language L and another language L bar. That means this is a language, means these are the, here we have a set of valid strings. Say, suppose that L is equal to 0 star. 0 star and L bar is the complement of this. Suppose that your input alphabet is say 0, 1. That means L is 0 star means 0 or more occurrence of 0. That means if you have a binary string which is having only zeros, that is called this language, and all other binary strings belong to this. All other binary strings belong to this L bar. That means L bar is the complement of L. L bar is the complement of L. That is, L is 0 star and this is sigma star minus 0 star. That means all possibilities of binary string, from that we have to exclude 0 star. Then you get L bar. And suppose that here for this L you are developing a machine, a Turing machine M. And suppose that W is given, this will be accepted, if this belongs to this language. That means if you are giving say 0 0 0, that will be accepted. Why? This 0 0 0 belongs to 0 star. 0 0 0 belongs to 0 star. That's why it's accepted. Suppose that if you are giving 0 0 1, what will happen? It belongs to this L bar. Why? It is not belonging to 0 star. That's why it is belonging to L bar, and that will be rejected. Okay. And a Turing machine which holds, generally speaking, in the definition of Turing machine, we are not specifying whether it is halting or not halting. Suppose that you have developed a Turing machine which always halts. Such type of Turing machine is called a Turing machine TM with halting. A Turing machine which definitely halts is called Turing machine with halting. And it is not having any problem with halting. And generally speaking, a Turing machine is, we cannot say whether it will halt or not halt. Whether it is, and we are not in a position to say whether it is halting, whether it halts or not. Suppose that our Turing machine, definitely we are sure that it will halt. That means, suppose that a string is given, it will say either accept or reject, or yes or no. Yes or no. If yes, that will be accepted, and if it is not a valid string according to our language, then that will be rejected. That means here, see, suppose that you have developed, this is for L. This is a Turing machine for L. That means this machine is accepting all strings. And suppose that you have another Turing machine. The same Turing machine M can be used for accepting this L bar also. Why? Here suppose that you are providing this input W, same Turing machine. In that case, here you are accepting. In that case, here it is rejecting and this is accepting. That means here acceptance means here rejecting and here rejecting means we are accepting. That means same Turing machine can be used to accept L bar also. L bar also. That means L is recursively enumerable means that can be accepted by a Turing machine. L bar can be accepted by the same Turing machine. That means L bar is recursively enumerable. L is also recursively enumerable. That means if you have a Turing machine which is accepting the language, a Turing machine which is accepting the language as well as rejecting the language, that means your Turing machine definitely holds. So if you have such a Turing machine, then the language accepted by that kind of language, that kind of Turing machine is called recursive language. One thing you should always remember: a language accepted by a Turing machine is recursively enumerable. If such a language is, if you have a Turing machine with a halting problem, such a Turing machine is accepting recursively enumerable language. But if you have a Turing machine which is halting, in that case, the same Turing machine can be used to accept its complement also. That means its complement is also recursively enumerable. Its complement is also recursively enumerable. That means if a language is recursively enumerable, there is a Turing machine which is accepting that. If its complement is also recursively enumerable, the same Turing machine can be used for accepting the complement also. That means if a language and its complement are both recursively enumerable, then we say that that language is recursive. Okay, that means if you have a Turing machine which is not having any halting problem, then the language accepted by that Turing machine is said to be recursive. Or in other terms, if L is recursively enumerable, L and L bar, if a language and its complement are both recursively enumerable, that language is said to be recursive. Okay, now we are going to discuss the properties of the recursive and recursively enumerable languages. Suppose that you have a language L1 which is recursively enumerable and M1 is the Turing machine for L1 and L2 are recursively enumerable and the corresponding Turing machines are M1 and M2. Suppose that we are going to check whether L1 union L2 is, and the Turing machine equivalent to that is M. That means L1 is a Turing machine, L1 is a language which is accepted by a Turing machine M1, L2 is the language which is accepted by M2, and we are going to check whether L1 union L2 is accepted by M. We are going to have a Turing machine for that, and our definition is L1 is recursively enumerable, L2 is recursively enumerable, and what about L1 union L2? If L1 is recursively enumerable, this is M1, and this is L1 is recursively enumerable means that is accepted. Yes, accepted. And we cannot say whether it is rejected or not. That means as per our definition, this is recursively enumerable. This when this M1 is having halting problem. If it is not having any halting problem, then you have a no also. That means it can accept as well as reject. But this is not having the capability for rejection. That means that will this is having the halting problem. That is looping. So here in this case, I am going to not going to draw that. Okay, that means if this is a valid string, that will be accepted. Okay, L2 is another language. L2 is another recursively enumerable language, and the Turing machine for that is M2, and the same input is given to this, and if it is yes, that means here suppose that this is the Turing machine M. Turing machine M1 is accepting recursively enumerable language L1. Turing machine M2 is accepting recursively enumerable language M2, and we are going to check whether L1 union L2 is recursively enumerable. That means here in this case, if W is given and ask for M1 whether it is accepted or not. If it is accepted, then yes, and it will check whether W can be accepted by M2. That is also yes, and the result is yes. That means combining these two. That means here yes, here we don't have any no. That means here this L1 union L2. That means if you are combining those two, taking the union of those two, you cannot say whether that can be rejected or not. That means if L1 and L2 are recursively enumerable, then L1 union L2 is also recursively enumerable. Okay. Now we are going to check whether these two are, suppose that these two are recursive languages. L1 is recursive, L2 is recursive. We are going to check whether L1 union L2 is recursive. L1 is recursive, L2 is recursive. Okay. See, M1 is, this is the Turing machine M1, and we are providing an input, and it will say either yes or no. And suppose that you have another Turing machine M2, same input is given to here also, yes or no. And now this is the equivalent Turing machine. Here we are providing the input W, and input W is provided, and using this M1 we are checking whether this is yes or not. That means if that can be accepted by the Turing machine M1, then definitely that will say yes. Yes. And here this no, that means M1, if M1 fails, if this Turing machine can be, if L1 union L2, suppose that an input string is given, and if that can be accepted by M1, or if that is asked for L1, then it will say yes. And suppose that when you are given here it is no, when this is activated, this line is activated, then this M2 is activated, otherwise M2 won't be activated. That means this no signal is acting as a switch here. If you are giving an input W, and that is passed on to M1, and if this W can be accepted by M1, definitely this box returns yes. If no, that means if this W is not a valid string according to M1, what will happen? This line is activated, and this is acting as a switch. Then this M2, this Turing machine will be activated, and now the input is given to this M2, and As per M2, if it is a valid string, then it will say yes or no. That means this is giving either yes or no. That means if L1 and L2 are recursive languages, L1 union L2 is also recursive. L1 union L2 is also recursive. And that's all about L1 union L2, and these are the important properties of recursive and recursively enumerable languages. Then you have to study three types of, this is a recursive set, recursive language. This is recursively enumerable but not recursive. That means recursive languages are a subset of recursively enumerable languages. When a recursively enumerable language is said to be recursive, that means if in a recursively enumerable language, if a language and its complement are a recursively enumerable language, then it is recursive. That means if L is this, L bar also belongs to this. That means if a language belongs to recursive, then definitely L bar is also in that recursive. That means there is no possibility for a language which is recursive and its complement is recursively enumerable. No possibility. If a language is recursive, definitely its complement is also recursive. Here, recursive but not recursively enumerable, but not recursively enumerable. The outer layer is non-RE. This is non-RE. That is non-recursively enumerable. So that's all about undecidability, halting problem of Turing machine. And in this lecture, I told you about the halting problem of Turing machine and undecidability. Undecidability in the sense, for some inputs, the Turing machine cannot say whether they can be accepted or not. That is undecidable. Those problems called undecidable problems, and a halting problem of Turing machine also explained. And I told you about recursively enumerable languages and recursive languages, the properties of important properties of recursive and recursively enumerable languages also we discussed. And this is the hierarchy. Recursive languages are a subset of recursively enumerable languages, which is in the outer we have non-recursively enumerable languages. Okay. With that, I am concluding this session on undecidability, halting problem, and properties of recursive and recursively enumerable languages. Thank you.